Cool, guys. We can get started. Today we'll be talking about a framework for heterogeneous ZK-proof aggregation, and this is a joint work which is done by me and my co-founder Nitanshu. Uh, we are working at Rize Labs. We are the founders, and we did this work together with Avail. If you know, Avail is a data availability layer, and this proof aggregation bit was used is getting used in their Avail Nexus platform, which is a ZK rollup for seamless interoperability. So yeah, let's get started. A little bit about me. My name is Rishabh, and I started Rize Labs in 2023, I guess. And before that, I was working with Goldman Sachs, and I graduated from IIT Kharagpur in 2021. So that's a little history about me. Let's get into it. And here are some of the topics that we'll be talking about. First, we'll be discussing what is the problem, and what is proof aggregation solving, a little intro to proof aggregation, and what's the difference between ZK recursion and aggregation of proofs. Some different styles that are there in the industry, which are being used for proof aggregation. And at last, we'll be explaining about our approach, which we took for Avail for regarding the ZK proof, validity proof aggregation. So, and a little disclaimer, this assumes that you guys have a little bit understanding of what ZK is and how snarks work and how stacks work. So if anything doesn't make sense, don't get panicked. We have a detailed doc over here. I'll be posting this link over here in the chat so that you can take a look. And this contains everything. Maybe this PPT is just a highlight of all the things that's there in the slide. So for deeper insights, you can take a look at the article. Cool. Let's talk about the problem first and why it's necessary for proof aggregation to be there. The first problem, there are many problems which aggregation solves, but here I have listed top three, which I feel are important. And the first one is the cost, because every computation which you do should be optimized for two of the things. The first is the computational space and the memory, and the second one is the computational cost. So the verification itself, most of you might be knowing that proof verification is also a computation. There is a series of steps that needs to be performed on the proof, and most of the protocols are verifying the Groth16 or the Plonk proof on chain using the Ethereum precompile 8, I think, and this was introduced just to verify the BN254. So there is a curve called BN254, and that is containing the pairing based operations inside it. So whenever we try to do a pairing operation like addition or a multiplication, that precompile is called, but that precompile has a cost attached to it. It's less, but it's there. And the verification of a usual Groth16 proof is around 300K gas, which is a lot if you are verifying a lot of multiple Groth16 proofs. So you cannot imagine like verifying 1 million proofs per day, because that will be really costly. I'm not remembering the exact figure, but till now we have paid like millions of dollars in just ZK proof verification on chain. That's a lot, and we can reduce this by using proof aggregation. And the second problem, which I feel, is proving a bigger computational trace whenever we execute a program. Let's say it's the verification of a block, let's say of an Ethereum block. So we know that there are a lot of operations over there, and it's not possible to have single computational trace proving everything. So what we can do is proof aggregation allows us to break that into several parts, as we'll see in the next slides, and prove them together. So whether you're executing a machine learning program, or let's say you're any hefty program you can imagine in computer science or anywhere, that can be broken down into several pieces, into several chunks, and several proofs can be calculated, and those can be aggregated together. So that is something which proof aggregation helps in, and that's the problem that we can solve through it. Also, at last, what proof aggregation enables us is combining different proofs. So let's say you have a storage proof and along with a validity proof. Is there a question or something? Cool. I'll move forward. If you guys have any questions, just drop them in the chat. Mitanshu is there in the chat, so he can try to answer, or we can take them at the end also, if whatever is best for you guys. So yeah, combining different proofs is very helpful because it helps us in composability. Like in our work, we are combining multiple validity proofs together, which allows us to make interoperability easy. And different proofs can be combined to and enable different assumptions that are there behind those proofs. So that is something which is also getting solved. So we are talking about proof aggregation. It solves everything, but what is it? Like a very high level overview can be that if you are having multiple Groth16 proofs, let's say, and you want to combine them together so that you can have one single Groth16 proof, let's say, or a Clong proof or any proving system of your choice. What you can do is you can create a circuit. As I mentioned earlier, like verification itself is a process which is an NP complete process, and that involves certain steps needs to be performed. You need to verify the pairings. You need to make sure that the public inputs are counted inside the verification process, and many things. So that all can be written down inside a circuit. And as you know, circuit can contain arbitrary programs, like right. So verification itself can be written inside the circuit, and that verification, what it does is basically verifies proofs serially, so that you can have, let's say, n proofs and all of them get verified if they are of the same proving system. But if they are of the different proving systems, then we need to take some different considerations, which we can look forward afterwards. So this is a very high level overview of like what proof aggregation enables. You can imagine it like a Boolean circuit, which I like to do is like you have different inputs, and those are providing let's say outputs of different programs are being executed and proved by different proofs. So every proof is one when the proof verification takes place, and at the end you get a one if every proof is verified and is valid. So you can imagine it like this. So like and recursion is also one thing which is very close to aggregation, but it's a little different. So you can imagine is like recursion is anything that you can have learned in computer science, like uh, executing a program inside another program. Like you have some conditions, and then you go inside, you create a new condition and go inside that until you hit a base case. So that is recursion. So something similar is happening in ZK proof recursion also. So you have a proof, and you take the circuit of that proof, your verification circuit of that proof. You do the verification, and then you do the computation also. The next step, let's imagine you have a computational trace, okay, and you broke down into three pieces. And you, for the first piece, you have a proof. Let's say you verify that proof inside another circuit, and the second part of the computational trace is also executed in the verification circuit. So now you can have at the end of the second step another proof, which basically says two things: that the first computation was correct, and the second computation is also correct because the first computation's proof was verified inside the verification circuit. Okay, and you can repeat this in the next step. Now you have the second step proof, which verifies all the proofs behind it over here, first and second. And now you can perform the third computation along with the verification of the second computation. And then you can at the end have a final proof, which proves the validity of all the three operations that you have done, or the bunch of operations that you have done. So this is like recursion, basically recursing over the different proofs that you have. So this is something similar to aggregation, which people feel like, but there is a slight difference. Like aggregation basically involves combining different proofs together, combining same proofs together into a single proof. And recursion is basically linear in fashion, where you have single proofs and then you recursively combine the verification of previous and the current computation. You can imagine it like it's also called incrementally verifiable computation. There's a very good paper you can read about it by Variant, and this is basically the definition of incrementally verifiable computation. In a linear fashion, you verify the proofs together, and then you finally have a proof which verifies this. I'll be explaining an architecture in the slides, which combines this recursion and aggregation together in a single protocol, which is used by RISC-0, and most of the industry standards follow that architecture for production grade proving systems. So, and yeah, there is a third component called composability. Composability is nothing but this is a simple operation when you, let's say, have a ZK star proof and you want to have a snark proof for that. So what you can do is, as I mentioned earlier, like every proof verification, whether it be a star or a snark, can be verification is a, as you know, is a process which can be performed inside the circuit. So you compose the star proof into a snark proof, and then you can basically, so for aggregation, let's say you want to aggregate different groth 16 proofs together, and you have different kind of proving systems before this. So it can take place that you have modified plong from zk sync. So zk sync uses a modified version of the plong, which they call boojum, and the second one can be ff plong, which zk avm uses, and zk starknet uses star proof only. So all these proofs are different kinds of proofs, and you cannot uh, aggregate them together until you have a single proving system, a single homogeneous proof, right? So what you do is, these are heterogeneous proofs, and these heterogeneous proofs can be composed into a homogeneous proof, which can be a groth 16 or a plonk or anything. Then you can compose them together. So this is one of the architectures which you can take, right? So yeah, this is just written what I explained earlier. Like recursion is something which you take two proofs together and have a final proof, and aggregation is like you take two proofs together and combine them into a final proof. Yeah, um, aggregation is something which can be done for different proving systems. And as far as I have researched, like there are mainly widely known three proving kinds of aggregation schemes. Like there is a pairing based snark recursion, and stark recursion, and folding schemes. So let's briefly discuss them. What I'll not be going deep, because each heading over here is a talk in itself. So you can refer to the doc that I mentioned earlier. I have tried to explain these things deeply over here. So you can take a look. And if you have any questions, you can get back to me after this. So aggregation with snarks is basic. So snarks are what? Like snarks verification is basically a bilinear pairing check, right? And the difficult thing about this is that the doing the bilinear pairing check inside the circuit is very costly, because it involves a lot of computation. In Ethereum, it's easy because you have the pre-compile, right? And that takes care of all the things. But inside the circuit, you don't have all the you don't have all these pre-compiles. You can have the pre-compiles with now ZK VMs coming out there. So, but in normal proving, like say you're using Circom, you cannot have pre-compiles over there, right? So what you do is you write the entire verification or the pairing check inside the circuit, which is very costly to combine the proofs together. And so that's why snark recursion is not preferred, and most of the zk vms are also not using snark recursion. Snark is mainly, so every proof system has a good thing and a bad thing, right? The good thing about snark is basically groth 16 plonk, all these pairing based proof system is that you can verify them on chain easily, and there is a minimal cost like 300K for a normal groth 16 proof, around 300, and that needs to be paid. But yeah, then you can get guarantees from ethereum itself or from any evm chain itself that you are verifying the proof. So that is something good thing about snark. But the recursion part or the aggregation part is not good enough because it's very costly. And then comes the stark recursion. The Stark is another form of proving system which you might know of, which is based on hashing, and it does not use elliptical curve pairings. That's why it's also called post quantum secure. So you can choose any hashing function, and there are Merkle inclusion proofs being checked in for a Stark verification. And have a understanding of snark and stark. So if you don't panic. If you just read about snark and stark, then these things will make sense. So stark is something which is used industry wide for aggregation processes, because Fry, which is the commitment scheme in most of the starks, is aggregation friendly, and pairing by linear pairings or KZG commitments which are used in snarks are not, as I mentioned earlier, because of the costs involved over there. There are some methods but I'll not be discussing them over here. So yeah, Stark is pairing friendly. So most of the production systems use them. And there is a third kind which is which was mostly discussed last year, folding schemes, which was introduced by Nova, which is a folding scheme based mechanism. And what you do over there, you have a similar kind of recursion over here, as you see. I can show it over here. So this is a folding based architecture, and where you have, as I mentioned earlier, you have the previous proofs and you have the current computation. You do that, but folding schemes allow you to have a uh, uh, what should I say, pre-computation between the real proving starts. So this is not folding is not really a proving step, because Nova also uses Spartan, which is a different proving system. And what folding does is like a pre-computation on the provings, which makes it lighter. So so this brief about all the three aggregation types. I don't think we have a lot of time, so I'll be quickly talking about one industry grade standard by Risk Zero. This is from the Risk Zero team. All the two things are combined over here. Like here we have a computational trace. So what happens is, like whenever you execute a program in ZKVM, all these ZKVMs create a computational trace, and that computational trace is converted into polynomials. So this is like the computational trace, and that polynomials are being created, and those polynomials are being proved using stacks, and those stacks are now recursively combined. So this is the recursion basically that's taking place until and unless we have a single groth 16 proof, which is basically achieved through a composability. As you can see over here, we have a star proof and we compose that into a groth 16 proof, and then you verify that groth 16 proof into a Ethereum chain. Our approach is something similar. What we do is, I'm not able to zoom, but yeah, we take the validity proofs. So our main goal was to combine different heterogeneous proofs of different validity proofs of different chains. Let's say ZK Sync and ZK EVM. We started with these two chains, and mPlonk and FFPlonk are the two proving systems which we have. What we do over here is we convert these proofs into a single proof, into a homogeneous proof. We fetch the proofs continuously from these chains, and then we combine these proofs together. We first convert these proofs into stacks, which are basically recursion friendly. We compose them, and then stacks are aggregated together to a single stack. And then we use composability again to convert the stack into a groth 16 proof, which can be verified, which this step is not necessary if you are not using an EVM chain. Uh, if you want, you can do that. If not, it's not mandatory. So if you have a final proof, then you can verify that final proof anywhere else, and yeah, you're good to go. Like you have the trust guarantees that these initial proofs have, and using the correct public inputs, as public inputs are flowing, through this supply chain, and at the end, if they are correctly attached to the final proof, then you have the trust guarantees that are there in the initial proofs. So yeah, this is the final architecture that we are using, and I guess if this is written just like the explanation what I mentioned over here. I guess that's it from my side. Like if you want more information, you can, I guess, read the documentation that I mentioned. It's also open source. The code is open source, so you can take a look. This is the repo. You can try to run it and see like the recursion. And, if you guys have any questions, then would love to answer them. And yeah, here is my QR. You can scan if you want to get in touch for any questions. And we are also hiring, so if you guys want any opportunity, would love to have a chat.